So Pei is going to be kicking off. This is kind of the primer. It's a presentation, but also a primer for the breakout session that we have after this. So Pei is going to be talking about the research priorities and looking at 2026. So how about Mike?
All right. Thank you so much. Welcome, everyone. I have to say that this every 6 months, our annual review meeting is my favorite time of the year. The reason is, it's great to see you, everyone, and also thank you for coming back every 6 months. And also, it's so good to see new faces as well. So, why this is my favorite time? Because produced water research is very important for our state, for our nation. And this is the time for us to reflect and then to review and then to see what we have accomplished and what are still the knowledge gaps. What will be our next step as a research plan and priority. So today, I'm really glad that following all our outstanding presentations and speakers, we will talk about some updates of research related to the produced water characterization, treatment, and reuse, and also our research priorities. When you see my presentations, I say, hey, Pei, I have the same thoughts. We already talked about it. I think this is exactly the point that we capture all our thoughts together because great minds think alike. So that is good. And also, I want to work with you all to look at your feedback, your input, because after this session, we will have the breakout session that Zach will talk about. You can tell us, are our research plan good? What should be the priorities? And then what are the knowledge gap? What else you want us to do? So for the consortium and for everybody's interest here is to convert produced water from a waste stream to resources. Resources including fresh water, purified water for fit for purpose applications, but produced water also has critical minerals and the valuable constituents that we can recover. We learned all from the previous presentations, but produced water treatment and reuse has to take an integrated framework. And this includes from the pre-treatment, desalination technologies to post-treatment. Post-treatment will allow us to meet all the water quality requirements for different applications for agriculture, land applications, surface water discharge, industrial uses. So through the consortium's research and the development, we work with all of you to evaluate the produced water treatment technologies. And especially I want to emphasize on the desalination technology. Right now, we are familiar with thermal desalination. Right now, several companies have tested the innovative membrane-based technologies, low salt rejection RO. There are other desalination technologies emerging that we have been testing, including electrodialysis and solvent desalination, membrane distillation that Sun Vapor has been working on, and Dr. Huiyao Wang at New Mexico State University is also working on photocatalytic membrane distillation, and Dr. Jian Jiayu with New Mexico Tech is working on innovative membrane distillation, and there is a phase fractional desalination followed by RO. So there are all kinds of desalination technologies we're developing. And also the post-treatment is very, very critical because there's still carryovers of these constituents, ammonia, boron, and others, VOCs, that we need to remove through the post-treatment. And post-treatment, even though people may say, hey, through NMSU's research publications, you demonstrated you have good removal of all the VOCs, ammonia. But in reality, because the produced water can be very site-specific, and depending on the technologies, some constituents carry over may not be easily to be removed. So, and also maybe the breakthrough curve could happen earlier, not as we expected. So, polish post-treatment is also critical. We can look at granular active carbon to remove organics, zeolite to remove ammonia and change air stripping, and also oxidation processes, biological treatment. So we are evaluating all of this. And through our previous presentations, that we know there are critical minerals in that water we can recover. And another one is ammonia. And Dr. Yan Zhang, Hui Yao, and even others were working on ammonia recovery and also the hydrogen. Because produced water is the water, and Hui Ya and his postdoc Tarek have been using the produced water for hydrogen production, and actually it can produce much more hydrogen from the produced water using the photocatalytic oxidation than using the brackish water, municipal wastewater, tap water. So it is great. Also, New Mexico State University received a grant with GIVE project through the EDD. Right now, we use a photocatalytic process to produce the hydrogen through a pilot project at the same time to recover fresh water. And also, you may know that if you look at the water composition in Permian Basin produced water, it is mostly sodium chloride type, even though we have some divalent ions, calcium, magnesium, some silica, sulfate. So after the treatment, recover fresh water, what do we do with the brine? And through the new study Lauren just presented and the Wall Street Journal, the Permian Basin is become a pressure cooker. So any water we can save for reuse or chemical production, it will be great. So this is a sodium chloride type. And then through some new technologies, we call it bipolar electrodialysis, we can convert sodium into sodium hydroxide and the Cl chloride into the hydrochloric acid. So in that case, we can have in situ use for pH adjustment, for boron removal. We need higher pH, we need sodium hydroxide. And also in the Permian Basin, we use a lot of hydrochloric acid for hydraulic fracturing. So through this technology, we can convert the waste stream into the chemical products. So I think there are a lot of potentials for us to utilize this produced water as a resource through this collective effort on science, technology demonstration, and the innovations. So for produced water treatment and reuse, how can we make sure this water is safe for reuse? We have EPA, NMPWRC, all the regulations, everybody, environmental groups, everybody. So we want to make sure this water is safe for reuse, but safe is a relative term, right? So we want to know what are the chemical constituents, even though we have some chemicals present, and how about the toxicology assays. So what will be the fate and transport of the treated produced water into the environment for surface water discharge, agricultural irrigation. So here we take a integrated approach using the targeted analysis, non-targeted analysis, and the whole effluent toxicity studies, humans, cell line studies, all the mice experiments, fate and transport modeling, risk assessment to evaluate the safety of this water. So we will talk about that tomorrow. We have the half-day presentations. So our research plan, even though this is modified research plan as compared to 5 years ago when we started, but the majority stays the same, is assess the key scientific and the technical challenges in produced water treatment and reuse, including all the characterization work, the toxicity study, risk assessment we talk about, and also evaluate the treatment efficiencies, pre-treatment, desalination technologies, post-treatment is a key for fit-for-purpose applications. So then we had a discussion for 2 hours to talk about the TA before your presentation. Sarah, when we had the meeting, you also said what will be the techno-economic assessment. And then from the industry, I will not name them, but everybody say, hey, Pei, we need a real world actual data for the economic assessment. So that is the work that we are going to do in 2026. And then all the data, all the information what we collected will be used to inform the science-based policies and regulations. Of course, we will support the public outreach, education, and rely on the collaboration with all of you to achieve it through the consortium, through all the working groups. So we are already very familiar with the NPDS class list. And so Dr. Yan Zhang and Dan and Ryan, we gave a webinar. If you have not watched the webinar, it is on the consortium website, it's on the YouTube. It talks about the history, how we developed the NPDS class list. So for this list, through the previous pilot testing projects, we sent the samples to the third-party commercial labs. We analyzed 17 categories of the constituents, from all the metals, radionuclides to volatiles, semi-volatiles, and even including dioxins, PFAS, and the whole effluent toxicity test. So the rest of the samples, we did all the analysis at NMSU, including non-target analysis in-house, so we can compare the notes with the commercial labs. And also we use non-target analysis, Dr. Simon and Susita William, they're all there through the Cal Lab. So we use the high resolution LCMS orbit trap for non-target analysis. So led by Dr. Yan Zhang and Ryan Ashley and Dr. Zhang Xu, and Ivy is there. We did all the wet test, human silence study, mice toxicity study, reproduction experiments. So all these are ongoing. We have accomplished a lot, but still all the results are ongoing. For example, every day when I meet Abby, I say, hey, how our mice are doing? Ryan is taking the lead. We have also all the graduate students, undergraduate students taking care of hundreds of mice right now. So it's very exciting. And for the fate and transport modeling, Dr. Renwei Li and Casey and also Heyday, they are doing all the fate and transport modeling and the studies. So all of them. And it's ongoing. We have accomplished a lot, but we will continue to work on this. Just some updates about non-target analysis, because during our biannual review meetings, Dr. Panhasa and Dr. Sloka, they are there, they presented it. So I just gave you a quick update. Because tomorrow for all the presentations, we will not talk about non-target. We will talk about non-target, but not targeted analysis. So this NPDS class list, over 400 constituents, we use it to monitor 6 thermal-based technologies and also 4 membrane-based technologies in the Midland Basin, in Delaware Basin, and including all the thermal distillation, membrane distillation, and the membrane-based technologies. So this is a summary slide. I know it is very busy. Different colors represent different categories of the compounds we monitored. But in total, we analyzed 600 constituents, and about half were detected at least once. Some may be detected consistently throughout all the treatment processes. Some may be only detected once, but that means we see different numbers. I think Mike has some numbers and Ryan has some numbers, but this is what we found through these 10 treatment processes. And after that, so Panhasa and Siloka, they did analysis on, so we classify them based on the treatment technologies. This may align pretty well with the ELG. It's technology-based treatment processes. So this is the thermal-based technologies. We look at all the constituents that we analyzed, we detected, and look at their properties, hydrophobicity, log QW, and solubility, Henry constant, to look at how we correlate their solute properties with their separation performance. And we also look at, can we have this surrogate parameter indicator ideas, because it is not feasible to analyze all these 400 constituents. They are very expensive. It's, you cannot get the results right away. So in this graph, all the colors, the green color shows there is good correlation between all these parameters. conductivity, pH, TOC, benzene, toluene, gross alpha, gross beta, PAH, so all of this. And then you see some has good correlation, some don't have good correlation. So with that, we can propose, for example, for the thermal-based technologies and the conductivity could be a good indicator for TOC and the sodium chloride, but boron and ammonia, they have to be listed as a surrogate compounds because there is no good correlation with other constituents. And also TOC is not a good indicator for BTEX. We have to list BTEX as indicator compounds. So this is some practice we are trying to come up with. This is for the membrane-based technology. And again, you see different colors. It shows a correlation between different parameters. And for the membrane-based technology, electrical conductivity is a good indicator for TOC and with sodium. And then also for the, for example, ammonia and the boron, actually, they are a function of the TDS and the pH removal. This is for the membrane-based. And right now, we are preparing the manuscript. One is based on the pilot testing results on the membrane-based technology, and another manuscript is on the pilot testing of the thermal-based technology. We plan to submit those manuscripts very soon. So, okay. Those are the desalination technologies, but we also know that the post-treatment is very important. This is just an example. Actually, we compare, these are selected constituents and compare with the drinking water standards. We have a very long list of the water quality requirements for fit for purpose applications. And then here we have the thermal distillate, and then what we have found in the thermal distillate. Again, this is a very short list. We have very, very long list of the compounds. And then you can see that even though like ammonia and boron are not in the drinking water standards, but those are the constituents critical for agricultural irrigation and for the aquatic life. And then through this thermal technology, we still have high ammonia in the distillate up to 120 milligram per liter. That is very high as nitrogen. We also have the boron, and then we also detected higher concentrations of the radionuclides. And then after the post-treatment, all these constituents are actually removed either to very low concentration or below the detection limit. And then now let's look at the membrane-based technologies. Again, we found some higher concentration of ammonia and the boron and BTEX, and then also the radionuclides. You see their colors are kind of red or yellow. And after the post-treatment, they will be removed to below detection limit or at very low concentrations. So again, it emphasizes the post-treatment is very critical. And based on all these studies, right now we have development of the surrogate parameters and indicator compounds. It including the tier 1 daily operation, kind of like temperature, pH, electrical conductivity, dissolved oxygen turbidity, and TOC. And that will help to help guide the daily operations. And then if there is the change of parameters, or if you see, okay, wow, the conductivity is very high, that means, or TOC, suddenly there is a spike, then you can do more detailed analysis to look at the tier 2 approaches that include the total dissolved solids and the total ammonia, boron, sodium chloride hardness, gross alpha, gross beta, BTEX, and the pH. So we can also add down whole effluent toxicity tests into this short list. And we also had the internal discussion, maybe we can use some surrogate parameter from non-target analysis into this one as well. So this is in progress. All right. Priorities. What do we do in 2026? The first one is we will continue to evaluate produced water quality and the treatment efficiency through the targeted and non-targeted analysis, including the pre-treatment, desalination technologies, and the post-treatment. Dan, you showed that we need a longer term and larger scale pilot demonstration projects. So hopefully we will get those. So we will look at the variability of the water to get more realistic data. I'm not saying that the current pilot project is not realistic, but if we only grab the samples in a few days operation, the results may not be reflected long term because there could be scaling and falling corrosion, a lot of other issues. And I'm also very grateful that NMED spent 6 hours with us last Friday. We have about over 10 faculty members, researchers to give the presentations. We also received the feedback from the NMED on our research. So for this year, and we will convert some of the non-targeted analysis into targeted analysis with the red flagged compounds. So those compounds could be resist, could be toxic, even though we don't know their concentration, but we should convert those into the targeted analysis to know their concentrations. And then we will collect and compare the purified, treated, produced water with other waters, such as the surface water, groundwater, and tap water, and maybe rainwater, storm water. And then we will continue the toxicological studies using the whole effluent toxicity studies and the long-term fish exposure. Tomorrow, Dr. Yan Zhang will talk about almost 98 days of long-term exposure of zebrafish with the treated produced water. So the results are very promising. We will continue to do the mice toxicity study and the reproduction study. Tomorrow, Dr. Zhang Xu and Dr. Ryan Ashley will talk about those studies. So that is continue in 2026. And also the feed and transport study, we will look at the transport of ammonia, volatile organic compounds, semi-volatile organic compounds through the column soil experiments under the unsaturated flow conditions with plants, without plants, and then there will be the modeling work. So tomorrow, Dr. Runwei Li, Heidei Chao, and Casey will give those presentations. So, and then Subanki, she will talk about the germination experiments and the irrigation experiments. Right now in New Mexico, we are doing this greenhouse study. I know Shane at Texas Tech, you are doing greenhouse study and field experiments. So I hope we will continue to work on that, evaluate the treated produced water on agricultural irrigation and also on the land application. And then we will apply the EPA tools. I'm so glad, we have been in contact with Shang and then to get the support from the EPA using the EPA tools for evaluate the risks of the treated produced water through the different exposure pathways to evaluate the human health impact using the regional screening levels and for the targeted cancer threshold to the 1 to the -5 and then 1 to the -6 for the children at the age less than 6 and then for the adults. So, Dr. Xiaochun Yin is taking the lead right now on that study. And also we use the eFast, the test, and the chem informatics. So right now, I know Mark is here and, ExxonMobil and Orion also mentioned about using the frac focus to identify the chemical additives. So Dr. Xuewei Du right now are also looking at the frac focus data. We look at the chemical additives in the Permian Basin and in the San Juan Basin for the last 5 years. The goal is to identify what are the chemicals added at what dose, concentration, mass, percentage, volume percentage. And then right now we are comparing the notes. What added in the hydraulic fracturing as process chemicals, what we have detected in the raw produced water through the monitoring data. And then after the treatment in the desalinated water, in the post-treated water, what are the chemical additives occurred in those ones? And then we will identify their environmental resistance and then their treatment feasibility. So we can propose if these would be easily treatable, and then what would be the impact for beneficial use, and is it possible if we can replace some of the chemicals through, look at their environmental toxicity. So these are ongoing. Hopefully next time we will present those results. Also, we are looking at the transformation of those chemicals. For example, right now we added the fluorinated surfactants. If we inject it to the ground, is it possible they could be transformed into other products? So even though PFAS compounds, we monitor those, we found very low concentrations in a very limited number of compounds, but we are interested in the transformation products. So that is the work we plan to do in 2026. Also, going back to the TEA, then we did not compare notes before this, but I'm glad that we are on the same page. So for the TEA analysis, we want to do is real world actual data, and with the validation through the field testing and also the lab experimental results to look at from the pretreatment. There are different processes involved in the pretreatment, desalination technologies, and the post-treatment. We have to take this as an integrated approach, and what would be the optimum treatment processes based on the water quality requirements for fit-for-purpose applications. So for this tool, I call it water quality driven TEA analysis. Then in the levelized cost of water, and then we will consider the capital investment, operation cost, energy, how much energy we need, what are the chemicals we use, and then labor, and then what will be the replacement, what will be the maintenance, and also energy sources. Do we need to use electricity? Can we use PV system? Can we use solar thermal? Because if we use thermal distillation, we use solar thermal systems, right? So that is, and can we use flaring gas? Natural gas. So we are looking at the energy sources, also waste management and disposal. What will be the volume and the mass of the solid waste, and what will be the liquid waste? What will be the cost to dispose this? And also sensitivity analysis, because even though right now we call the vendors, say, hey, how much does it cost for the membrane processes? For ceramic membranes filtration, we get the number, but there is still the future technology advancement. We can do some sensitivity analysis. If the membrane cost is reduced by this much, what will be the cost? If we use in situ chemical production for acid base, what will be the cost? And also the life cycle time. Do we expect the return time of 3 years, 5 years, 10 years, 30 years? And also the economy of scale related to how about 100,000 barrels of water, or a million barrels of water. So through the sensitivity analysis, we can address those questions, and also the benefits. If we use this water, what will be the benefits related to it? How about the brine valorization, resource recovery? So with that, that will be included in our TEA analysis. So I know we talk about the modeling approach. So then I'm very grateful you get into the details of our research, actually. So those are based on the modeling approach. And I know, like Shane at the Texas Tech, you will use the water tap. And then we are involved in the water tap. I think NMSU team, we contributed maybe 7 modules to the water tap. It's hosted by the NAWI, National Alliance for Water Innovation, led by NETL. I think we have a new postdoc, Jordan Zhang, and he did his PhD at Columbia University. I think you contributed maybe 6 modules to the water tap. So we will use the water tap as well. But, mostly we will use the real field data experimental work to validate, to do the TEA. So with that being said, all this data, transparency, and the sharing data and the information will be used to support the regulations and the water policy with all the the constituents characterized in the raw produced water, in the treated produced water, in the post-treated water, and their separation efficiency through these treatment processes, concentrations, and their toxicity impact. And also, we will develop the indicator compounds and surrogate parameters. And then we will also estimate a protective maximum contaminant level as a reference number. You know, if we say we use this water for different applications, what would be their concentrations? This would be based on our produced water characterization, toxicity study, and also the data in the literature, in the EPA database. So with that, we will continue the baseline study. So we will also support the public outreach and education. As I mentioned, I think Zach mentioned several times, eventually all this data, including our published data and the raw data, will be in the consortium website. If you click on certain site, you will see all these raw data. And then if you want to understand more, you will go to our published peer-reviewed publications. So I want to thank all of you, really. It's a great pleasure. It's a great honor to work with all of you. Thank you so much for your contribution. I also want to thank all the NMSU researchers, faculties, students, even administrators. You see that this year we have made so much progress in our web development and public outreach. So I want to thank all of you for that. And the state of New Mexico, NMED, and the higher education department that contributed so much to support the consortium. And so that's how, with this funding, we can do all this research. And the EDD, OCD, OSC, Agriculture Department and Health Department, US EPA, Bureau of Reclamation, DOE, and the Texas Consortium, Colorado Consortium. So in one word, every one of you, I want to thank you.